This is 3 gamma, and we're going to begin. You're on the PDF, and this question's here, just to point this out to you. You'll see these. I'm going to focus more on these when we're back in the building, but these questions are in the back of the book. And generally speaking, well, you know this. These are in the back of the section. The 6 standardized test questions. So at the front of the PDF, I will put one of those 6 for you to read and think about as you're doing this. Like, what does a horizontal tangent mean? Okay, I understand. I get that. So would this thing have a horizontal tangent, meaning the slope of the derivative is 0? Is there any time that that could happen? And then as I'm thinking about that, as we're doing the work, your subconscious will be working on the problem as we proceed through the example. So here's what's happening. We're going over example 5, which is the bottom of page 120. And if I go here, this is the quotient rule. It's in the tan box on page 120. And what are we saying? You're taking these two functions and you're dividing them. You've got u equals something and v equals something. And you want the derivative of the quotient of the ratio of those two functions. Here's what you get. How do you get it? You get it from the difference quotient. So when it says proof of rule 6, just look here. In your T-chart, you would have, on the denominator, you'd have x and x plus h. When you subtract up, the x is added to 0. In the y column, you would have this u divided by v, and then you would replace x with x plus h, and v with x plus h, and you would subtract up, and you have this. And you go from here to here, they took this h and rewrote it as 1 over h out front, and they bow tied the top. You should be able to follow this. This is not something you're accountable for, but it goes to the depth of your understanding. And then we go down here. Here's the exact same technique that you saw on Tuesday. They inserted 0, negative, v of x times u of x plus positive v of x times u of x. And the reason they inserted 0 in there was to help them when they grouped the terms. Bottom line, what you care about is this. The product rule from Tuesday is commutative. It doesn't matter which function you call u and which you call v, because you're multiplying and there's a commutative property of multiplication. Then you're adding. Use the commutative property of addition. But for division, it does matter. So for the quotient rule, and this will seem confusing, especially today, the first time you see it, but I assure you, you're going to have to use the quotient rule for the next 7 months, and this will be, this is not challenging after this weekend. So what do? You take the denominator, which was v, and you go to your derivative and you paste it, and you square it. So I have u divided by v, so I have v squared in the denominator of my answer. But I take that same term v and put it in the top, in the numerator. And I multiply by the derivative of the numerator. Then I subtract the numerator times the denominator. So in some ways, the numerator is similar to the product rule, except order matters because it's subtraction. Okay? You don't need a formula sheet for this. I mean, it's open book for now, but you have to understand the quotient rule, and you'll use it so often that it won't be hard. So here's the example 5. And you have this. You have x squared plus a negative 1 divided by x squared plus 1. And you want the derivative of that. So if I go to the calculator, you got x squared, take away 1, divided by x squared plus 1. and I push zoom 4, there's the graph. You want the derivative of that graph. Well, there's some things I can tell. Ready? It's falling and then rising. Like, think about what this is saying. As you go to the right or the left, these ones have little to do with what's going on. Like, what's powering this thing is x squared. It's overwhelming the -1, and the x squared in the denominator is overwhelming it. So these things are going to 1 from the left and the right. That's the limit. Like if I went here, okay, 1 is a ceiling for this graph from the left and the right. When I get out of here and I turn on the derivative, because I'm going to use this to match up after we do the work analytically. Push graph. Does this make sense? I think so, because look what happens. In quadrant 2, well, to the left of the y-axis, the parent graph is falling the entire time. And the orange graph, the derivative, is below the x-axis the entire time. It's negative. To the right of the y-axis, the blue graph's going up the whole time. And to the right of the y-axis, the orange graph is above the x-axis. It's positive the whole time. So that's a logical picture for the derivative. We just have to analytically find the derivative. This is a non-calculator question. So here's the procedure. I take the denominator, I paste it down here, and I square it. I take the same denominator and paste it in the numerator and multiply it by the derivative of the numerator of the parent graph, which would be 2x plus 0. Subtract, other way around, the numerator times the denominator, which gives us this after we combine our like terms. 4x divided by x plus 1, the quantity squared. So we go back here. 4x, now you don't need the parentheses, but it doesn't hurt to have it in the numerator. Divided by x squared plus 1 quantity squared. What we care about is if y2 and y6 give us the same t-chart. And they do. So that t-chart is confirming that this calculus and this algebra is accurate to take you to there. Okay? So this is your model, and you're going to go to problem number 19. I'm going to leave this up here. For 19, you want to expand the numerator first. So to expand the numerator with a lattice, you would have x take away 1 I'm not going to do the whole thing for you. I'm just going to use start. X take away 1 times x squared plus x. Wow, it's an awful x. Plus 1. You fill in the cells and combine your like terms before you apply the quotient rule. So I could do that for you, but I think it's good for you to have some practice. So here's what we got. We take the denominator, x cubed, and we paste it in the denominator for the derivative. And whatever we paste it there, we square it. paste the denominator at the top in the numerator and multiply it by the derivative of the numerator of the parent graph, which would be 3x squared by the power rule, 3x squared plus 0, or subtract 0. Subtract, order matters, the numerator times over the denominator. You distribute this, combine your like terms, and you get this. And you could do this. You could put, ready, your answer here in y2. I've got it in y4 there. It doesn't matter. I typed the original question, in case I made a mistake, the original question in y1, and you see that y2 and y4 match up. You do have a discrepancy at 0. And that reminds us from the beginning of chapter 3 that numerical derivative function is not infallible. So the numerical derivative, y4 thinks this is a 0. But it's actually, you can tell in the derivative that x couldn't be 0 because you have 3 divided by 0 to the 4th. Okay? Example 6. Now, example 6, we're not going to do this. I'm just going to call your attention to it. On page 121, this has been on the AP test. And sometimes people freak out because they just give you this. It's actually a layup, if you understand what you're being asked. It says find y prime of 2 given these values. I think it's kind of hard to read that. So I just went ahead and said, build a table. 2 is the input. That's what they're telling me. Instead of reading all those function values, and then you're just putting the values in the expansion. Okay. So example 7, we're here. And look what happens in example 7. Here's the question. And you look at that and you think, oh, quotient rule. You got a quotient, you got a ratio of these two functions. But what did they do? When they did this problem, they gave each term in the numerator its own denominator of 2x. So they created a situation where the derivative of the sum is the sum of the derivatives. And they did it by the power rule. And the reason they did it by the power rule is because they're showing you the power rule works for negative powers of x, which you probably assumed it did, but the proof depends upon the quotient rule. So in the textbook, they just took these two parts of the sum and differentiated them individually. You could have used the quotient rule, you would get the same answer. It says right here, we could find the derivative by the quotient rule. At 1, well, if we put 1 in the function, the output's a 2. If we put 1 in the derivative, the output's a -1. So we're here. The only thing you were given is a 1. The height from the function is a 2. The value of the derivative at that point is -1. So you just do this. The parent graph to the tangent is y equals -x, and it's been slid 1 to the right, up 2 by doing the opposite. All right? So that's your model for you to go and do problem number 27. I thought I had that pause and I didn't. Okay, so here's what we're looking at. I take the denominator and I square it. 2x, the quantity squared. I take the denominator and paste it up here. The derivative of the numerator would be 3x squared plus 0. Subtract. The numerator times the denominator would just be a constant. Multiply these together, distribute the 2, combine your like terms, you're here. So the question says, when x is 1, If I put 1 in here, 1 cubed is 1 plus 1 is 2, over 2 times 1 is 2. The height would be 1. If I put 1 in the derivative, I would get 4 times 1 cubed, take away 2, which is 2, divided by 4 times 1 squared, which is 4. 2/4, 1/2. So I would have 1/2, y equals 1/2 x, be the parent of the tangent graph, and I would slide it 1 to the right and up 1. So visually it looked like this. X cubed plus 1 divided by 2x. The blue graph is the parent graph. The orange graph is the derivative. Does that make sense? The blue graph, x cubed plus 1. I took that right. Oh, sorry, not right. Did what I don't want you to do. Said input 2x, the denominator in parentheses, because this is divided by 2 times x. Second insert, parentheses. I made that mistake on purpose, so you would see it. Not really. Okay, so here's the parent graph. There's the derivative. This makes sense? Well, let's look, without doing the whole thing, let's look just to the left of the y-axis. The blue graph is falling the entire time. The orange graph's below the x-axis. To the right of the y-axis. The blue graph's falling. When it's falling, the orange graph has a negative height. When the blue graph is rising, the orange graph has a positive height. Back here, see if our answer matches what we got on the calculator. So our answer was 4x cubed take away 2 over 4x squared. Now, I don't care about the picture right now. I just want to see if the t-charts match up. They do, so the derivative is calculated correctly. So now I go back here. I don't need them both on. I'll turn on the parent graph. Now I'll put in the tangent line, which is 1/2 x take away 1 right? I moved it 1 to the right, up 1. There's the tangent line, and it's tipping the graph at the point, 1 to the right, up 1. Because the slope of the blue graph at 1 is the height of the orange graph at 1, which would be 1/2. Okay? So, example 8, which we're not going to go over problem 33, but example 8 is saying to you, you can continue to use the power rule. Meaning we've got this parent graph, here's the first derivative. Well, we differentiate that, you get the second derivative. You differentiate that, you get the third derivative. The fourth derivative, the derivative of constant 0. So differentiation is like sunscreen. You can reapply it. Okay? Now,